Ever pondered over the kinds of transactions node operators handle? They are the unsung heroes of the blockchain world, ensuring smooth transactions across networks. But not all transactions are created equal. They vary significantly across different blockchain networks. Today, we delve into these differences. In the blockchain universe, node operators often facilitate ordinary transactions. These are the bread and butter of the blockchain world, involving the transfer of assets from one account to another. Each transaction requires validation and inclusion in the blockchain. These transactions typically involve base 58 encoded addresses, the amount to be transferred, and a transaction fee or gas paid to the miners or validators. Node operators who participate in proof of stake or POS consensus mechanisms perform staking transactions. They lock a certain amount of the network's tokens to participate in the validation process and earn rewards. The terms of staking can vary from one blockchain to another. After the staking period, or when the node operator decides to withdraw their stake, they perform an unstaking transaction. On some networks, nodes can participate in reward mechanisms separate from block validation. This might involve locking tokens into a network program to earn additional rewards, known as investment transactions. If a node wants to withdraw their funds from an investment position, they would conduct a disinvestment transaction. Node operators can claim transaction fees and potentially additional rewards depending on the number of signatures or endorsements they've accumulated, following the network's claiming mechanism. Not all blockchains are created equal. Bitcoin transactions mainly consist of ordinary transactions. Ethereum supports ordinary transactions, smart contract interactions, and staking as it transitions to Ethereum 2.0 and POS. Solana supports ordinary transactions, smart contract interactions, and staking with its proof of history system. Arbitrum, a layer 2 scaling solution for Ethereum, involves validating and executing smart contract transactions without its own native token for staking. Aptos uses staking transactions with its Move programming language for smart contracts. Node operators on different blockchains manage a variety of transactions depending on the network's consensus mechanism and tokenomics. They are the backbone of the blockchain world, facilitating transactions, validating blocks, and maintaining the security of the network. The world of blockchain is as diverse as it is fascinating, and the role of node operators is central to it all. While Bitcoin focuses purely on POW mining and ordinary transactions, networks like Ethereum, Solana, and Aptos involve a POS component, allowing nodes to stake, while also processing complex smart contract interactions. Arbitrum primarily serves as a layer 2 solution to Ethereum and does not natively engage in the staking processes. Each blockchain has its own unique mechanisms for providing network security, processing transactions, and offering rewards to participants. In the burgeoning world of decentralized applications, dApps, the nuanced details of transaction development are pivotal to the success of a project. The Transformers chain, with its unique take on blockchain technology, offers developers an array of transaction types to leverage within their applications. This article provides an in-depth guide to assist dApp developers in understanding and utilizing the distinctive transaction types within the Transformers chain ecosystem. Briefly introduce the blockchain's importance to dApps and the emergence of the Transformers chain, emphasizing its distinction from traditional models like BTC and ETH. Ordinary transactions definition and use case. Explain what constitutes an ordinary transaction in Transformers chain and how dApps can integrate this functionality for asset transfer purposes. Development considerations tours. Fee mechanism. Understand the gas fee computation and its impact on users. Optimizing transaction speed. Techniques to improve the efficacy of transactions. Error handling. Anticipate and manage transaction failures. Staking transactions. Concept and relevance clarify the necessity of staking transactions on the Transformers chain and its significance for dApp engagement strategies. Developers' strategy staking amount. Comprehend the implications of the required staking amount. Smart contract integration. How to automate staking within your dApp. Security measures. Safeguarding staked assets through secure coding practices. Unstaking transactions. Mechanics of unstaking. Describe the process of unstaking as it relates to time constraints and limitations within the Transformers chain. Developers approach unstaking protocol, embedding unstaking functionalities within dApps. User experience. Streamline the unstaking process to enhance user retention. Investment transactions, operation and opportunity. Discuss the mechanics of investment transactions and their potential for incentivizing user participation and growth. Development blueprint, minimum investment thresholds. Incorporating these rules into DApp logic. Reward distributions, code algorithms to fairly distribute bonus rewards. Disinvestment transactions, understanding disinvestment. Set forth a comprehensive view of the disinvestment process on the transformers chain. Implementation tactics, withdrawal workflow, ensuring a smooth disinvestment experience for users. Updating user balances, real-time tracking and display of user investment balances post-disinvestment. Claiming rewards, reward system overview. Illuminate the reward system structure, including the claim mechanism and how DApp developers can benefit from it. Development strategy. Automated claim. Functionality, how to implement an auto-claim feature that operates within network rules. Displaying potential rewards, providing transparency to users on their pending rewards. Transaction confirmation and security blockchain confirmations. Explain the necessity of transaction confirmations and ensuring that your DApp accounts for the required number of confirmations for each transaction type. Security best practices, transaction signing, secure methods for signing transactions within your DApp. Private key management, keeping user keys secure while enabling transactions. Error management and exception handling predictable challenges. Identify common transaction-related errors and how to handle them within your DApp to ensure a smooth user experience. Exception handling code, robust exception handling, crafting your DApp's code to handle various transaction failures. Coding standards and best practices. Adherence to standards. Discuss the importance of code readability, maintainability, and compliance with established Solidity or Move standards, depending on the transformers chain's smart contract language. Code testing and audits, testing transactions, rigorous testing methodologies for transaction-related code to ensure reliability. Security audits, the role of external audits in affirming your DApp's security posture. User experience and interface design, UI/UX considerations, delve into the integration of transaction functionalities in the user interface, ensuring a seamless experience. Feedback systems, real-time notifications, keeping users informed throughout the transaction process. Transaction history, implementing a transparent and accessible transaction history log. Conclusion, reiterate the importance of a deep understanding of transaction types in the development of DApps on the transformers chain and the potential for transformative user experiences.